Is being recorded. So with that introduction, Dennis, take it away.
All right, Al, thank you very much. Can everyone hear me okay in the studio audience?
Yes.
Yeah.
Wonderful. Al, congratulations. You're the first person ever to make use of my Rate My Professor page in order to introduce me for a talk. I will say, as a brief deflection from this, the whole Rate My Professors thing was an offshoot of what used to be called MTV, I think, when they played music videos. And they actually saw my reviews, and they were so used to people being hated for their reviews, they couldn't figure out why everyone liked me so much. And so they actually came to Temple and did an interview with me on something called Professors Strike Back, where I actually got to sit there and just talk with them. And I was able to subject everyone to my earthquake dance. And there are some of my former students now under the employ of PA Survey, Chris Ost being one, who might be able to talk to you and show you my earthquake dance, should he be so inclined. So, anyway, again, thank you all very much for inviting me to give this presentation. Sorry I could not be with you in person. What I want to do here this evening is I want to bring you something, I want to bring something to your attention that's been bothering me for a while as I've been looking at these Devonian strata throughout the Appalachians. I'm going to focus in on some terminology in and around the Catskills, but this is really something that's going to apply all through the Appalachian region and down at the Virginia, West Virginia area, and of course also through Pennsylvania. So what we're going to do here with this is, first off, here we are out in the Catskills of New York. Here's one of my former very excited grad students to point out an ancient soil that he sees here preserved in the geological record. And like him, I'm very excited about these things because they have great interpretive power for the geological past. So what we're going to do here is we're going to talk a little bit about the very basic geology of what I'm just going to call the Catskill Wedge, or just the wedge. We're going to talk about paleosols, soils in general, some of the said strat issues that we have associated with this stuff, a wee bit about paleontology, and then also why is the Devonian such a critical period in time for us to be concerned about? We'll talk about the problem at hand and then hopefully a potential solution. And so this talk, while there may be a few things that may be new to the studio audience, this is also a plea for help from my standpoint. Some of you who have heard this talk or various versions of it at national professional meetings may go, oh, this again? But it's good to get the information out there again, just because we are looking for warm bodies to get involved. And so let's go back to the Acadian, and where we have convergent tectonics leading to volcanism, mountain building. And what's going to become more important for us is we're going to get this foreland bulge within which sediments are going to start shedding off into the foreland bulge shallow sea area. And for right now, I'm focusing in up and around New York State, but where the little tip on the dot is, the Catskills right there. That's where we're going to be taking a look at right now. And then we'll be spreading ourselves down farther to the south and west along the Appalachians. Now, this convergent tectonic episode produced a lot of terrestrial strata that was dumped into the Appalachian Basin during the Devonian, which, I mean, some of this stuff is up to a couple of kilometers thick. And so, stored within these strata is a detailed archive of the evolution of ancient terrestrial ecosystems during what I would argue is a very critical time in Earth history. We've got the stabilization of landscapes with vascular plants. We've got critters coming out of the water, exploring the land, and we're going through a pretty big change of ecosystems in general. And so that's what I want to explore with some of this stuff, or at least think about how can we get at it by looking at these strata in the Catskills and the Appalachians, within the Devonian. And so here we go. Here's all these classic strata prograding out into this foreland bulge area. And again, because we have convergent tectonics and subduction, one of the other big byproducts we have from this is a lot of volcanism. And we know we have bentonites all through the Appalachian Basin out here. We find them in the marine section. We're also finding them within the terrestrial. And I'll come back and I'll talk about that as to what kind of influence this has on the ancient soils that we have preserved. But it's also going to lead me down a path of a possible answer or a potential tool that's going to help us address some of the questions I want to ask as we go through this. So, the other aspect that I want to put in as part of just a general background is that if you go to the tectonic front and all these sediments that are being shed off of it, what we have here is a very cartoon diagram of what I would call a isochronous landscape. Now, I just saw a note coming in from someone saying they can't see the presentation. Is that true for anyone else online? If so, then I don't know if there's any kind of setting, Al, that I need to hit.
No, we can see you just fine. I'm not sure what
There's
the
one
issue
person,
is.
Maria says that it can be seen.
Yeah,
And
that sounds
see
like
it
a
from,
individual user problem. I think we can proceed.
okay, alrighty, very well. So the other idea that I want to get across as a background bit of information is from proximal to distal along this alluvial plain, I'll call it. This is an isochronous landscape. Things are going on all across it. But as you go across any landscape today, which could be considered isochronous, as you drive east to west across Pennsylvania, you'll see different types of images. Or I'm sorry, not images. You'll see different types of landscapes, different environments that all exist at the same time. But what we're going to do is we're going to investigate how this manifests in the geological record where we can't see all these landscapes at once. So isochronous landscapes, proximal to distal, but also proximal to distal with respect to any stream bodies that might be there. So here we go. Why are these deposits so important? The Gilboa Forest, which has been, we've known about this for quite some time now, to where it preserves stumps of trees that we've been able to mine out and also put into museum displays. So that's one of the more famous things that we get out of the paleobotany aspect of the Catskills. But also within the recent past, in one of the quarry operations in near the town of Cairo in New York, we actually exposed a full-on fossil forest with different types of trees, and I'll be showing you a plan view of that here in a little bit. But what I want to get across is that there are some very important sites within the Catskills that preserve beautiful evidence of paleobotany. And then also, if you get up into north central Pennsylvania, the famous Hindered, Pennsylvania, or Red Hill site, which preserves a lot of fish, insects, other critters trying to come up onto land. And so within these terrestrial strata, we have these individual archives of both vertebrate and botanical evidence representing, things that are going on in the Devonian at this time. And that's all fine and dandy. Um, but interspersed with all these things, these individual sites of either a forest floor here or the Red Hill paleontology site for the vertebrates, what we have throughout the entire wedge is thousands and thousands of meters of individual land surfaces that have been preserved in the geological record. Lithified soils, or what I refer to as paleosols. What we also see within here is we have full-on continental conditions I'm going to be talking to you about. We also have transitional soil forming conditions meeting up against the ancient oceans that were there. We're also going to talk about the influence of volcanism. So let's go ahead and get into this some. And I don't know how many of y'all like coffee. For me personally, as a professor and as a father of two young kids, without this, nothing else happens throughout my day. But what I want to do here is I want to use the concept of a coffee pod to bring forward the idea of how it is that soils form. So when we look for this, we start off with a big batch of water, a nice big batch of coffee grounds, and with the heated water moving through here, the hot water mixes in and starts to transfer the location of the ingredients of that coffee down into the carafe. But what is it that we're transferring? It's the flavor, the colors, the caffeine, most importantly. But what I would also have you think about is this. At the bottom of your coffee cup, what do you commonly find sitting down there? Silt or sediment, because it's also physical matter which is being brought from the upper part of the coffee pot maker downwards. Okay, soils in the natural environment are just the same way. So we've got this cartoon soil, it's raining. We are leaching and percolating chemicals in solution, physical particles down into the soil. And over time, what this is going to do is to establish a very distinct series of zones, what we call horizons, that pedologists look at and describe in order to try to understand how the soil is doing its thing. Now, what's really nice about this is through the study of modern soils, we have found out that there's five main things which influence the formation of soils: the climate, the organism's relief, parent material, and time, creating a very unwieldy acronym called work, based off the work of Hans Jenny back in 1941. And so is it hot? Is it cold? Is it wet? Is it dry? Is it top of the hill? You're on the side of the hill, you're the bottom of the valley. All of these different things influence the type of soil that's going to be formed. And if you were to go out and either dig a hole anywhere in your yard, your neighbor's yard, wherever, you will notice that there's going to be a vertical succession of distinct bands that we call horizons. The top of the soil is where things are leached from and percolated downwards. And in the middle of the soil, something we're going to call the B horizon, is an area where this stuff accumulates. What's really nice about this is by studying modern soils and the processes that are active, what we found is that sometimes we have additions to the soil, sometimes losses, sometimes we're transferring the location of things, either up or down, and sometimes we're transforming. So all of these processes of soil formation then create what I like to call a sphere of influence, because these things are forming at the land surface. They are trying to reach equilibrium. These are nothing more than geological materials that are breaking down under present day Earth surface conditions. So we have the influence of all of these spheres, the geosphere, the biosphere, the atmosphere, and the hydrosphere, that help to form the soil that we see. But what's nice about this is the soil, as it's forming, encodes and preserves its own history of formation and the products that were generated by these various spheres of influence. Now, we bring all this up to modern day soil taxonomy, and what that gives us is this. Across the United States, there are 12 primary types of soils that the U.S. Department of Agriculture recognizes. And you can see these as color codes. I'll point out right here the Great Plains, the grasslands, the prairies, the Midwest, Pacific Northwest with the Cascade Range, and a whole bunch of volcanic influence up here. And then I would also bring this to your attention right through here. And so my quiz question I always ask everyone is, what is this right through here? And I usually get the answer of, well, that's the Appalachians. Well, no, it's not the Appalachians, but it is the soil forming effect of relief that is giving us a certain type of soil that is very prominent in what we know as geologists to be the Appalachian system. So, given our modern understanding of what soils are, how they form, the processes that are active, and the products that are generated, what we can do is we can sit there and we can see beautiful changes just in the macroscopic in things like colors, the numbers of horizons we might be seeing. And here is the Jersey Pine Barrens right here, where we have the effect of a certain type of vegetation with very acidic plant organic acids coming down through the soil and mobilizing elements like iron and aluminum, which aren't normally mobilized. And so by understanding the modern 5 factors of soil formation and how they do their work, what we can then do is we can start applying this in a very much a uniformitarian kind of concept into the geological record to start looking at ancient soils preserved in places like the Catskill Wedge. And so I want to take a couple minutes here just to show you some of the features that I look for or some of my students look for when we're out into the field. Um, and one of the first things that will strike you, and here we are in the Catskills proper, some full-on Devonian, one of my intrepid grad students here looking for evidence of soil formation. But my my question I always ask myself, or I ask to my students, is what do you see? And the big takeaway from this is notice we have channel sandstones, fluvial channel sands, and a typical finding upwards fluvial package. And at the top of each one of these packages of overbank material are roots and other structures associated with the formation of soils. So in the Catskills, since everything pretty much has the same diagenetic red coloration, look for things like erosional relief and look for the areas that aren't as resistant, and you'll start finding some soils. Look a bit closer, and you'll start seeing root traces. This one happens to be infilled with clay, where the original organic matter was oxidized away, and clays took the space. Or sometimes you might see these greenish, ghostly traces, referred to as drab halos, which represents the in situ destruction or organic processing in anaerobic conditions, the decay of these roots beneath the water table. Um, and so we have all this evidence that we're seeing of roots, of soils in the grand scale. But as you look a bit closer, you start to see weird things like these polished, slick-sided surfaces. These are not tectonic. They're soil generated. And this type of soil generated feature is going to become very important within the story of the Catskills. And I will get to them here in a second. And so, any particular soil profile that we see in the Catskills, we can define the bottom by where we start seeing the original bedding of any sedimentary depositional process. We see a general finding upwards because a lot of this stuff is influenced by fluvial processes. But then we also see these vertical cracks right here. You start seeing some cracks coming across like this and a general blockiness. What within the geological term, when I was growing up and learning about geology, that's a blocky mudstone. You might have heard the term Hackley that gets used a lot. These are ancient soil form features called PEDs, three-dimensional chunks of soil. And there's other things coming down through here, which I would need to zoom in to show you, but there's roots here, everything that's just screaming, wow, this is the surface of exposure, then covered by the next depositional overbank event, in this case by a thin sand, which then shut this off from pedogenesis, put it into the geological record, allowing it to be preserved and studied today. So what we're going to find, or what we're going to talk about here within the Catskills, is I'm going to take you through three different areas along, we're just going to assume it's an isochronous land surface. We're going to go from proximal, we're going to go to distal, and then in addition to these variabilities, we're also going to talk about what's going on just through time in general. So across the wedge we go to take a look at some of the soils that we have found. The names of these are not important. What I want you to realize, though, is just by looking at the legends, like here's some sands, here's some shaly materials, here's some mudstone materials. What I want you to get out of this slide is that in this one area, possibly about the length of a football field, I was finding 3 or 4 to 5 different types of ancient soils, all in one section exposed along a road cut. And the concept I want to give to you is this. If you drive along, again, let's say from the coast of Jersey over to Pittsburgh, you're going to cross a lot of different environments of soil formation. We commonly use the term in the rock record of facies to describe this three-dimensional body of rock and associated fossils representing a particular environment of deposition. What I would have you think about is the term pedofacies. These bodies of ancient paleosols that represent particular pedogenic environments. And in essence, we can also apply almost a Walther's law-like approach because different soils across a landscape will be adjacent to each other and will slightly change depending upon changes in topography, in drainage, plant communities. And so we can take this Waltherian approach to the soils we see stacked in a vertical sequence as a representation of soil environments that are present within this ancient environment at that time. Also, as we look at this, we can go proximal to distal from an orogenic front to an ocean. We can also go proximal to distal with respect to any individual stream. And what we find is depending upon where we are on this proximal to distal floodplain, we'll see either increasing or decreasing amounts of soil formation, sedimentation, and the degree to which water table fluctuations will affect the morphology of that soil. And so what I have down here in the bottom are the names of 3 different types of soils that can be found in a modern setting. Entisols are baby soils. Inceptisols are just a bit more grown up. And then alfisols, think of these as your forest soils across the Midwest, Ohio, Indiana. They're clay rich in their middle, forest growing on top, humid, temperate types of soils. But this relationship that I have diagrammed here, we see when we map out soils in any part of the United States across all of our land surfaces. So as we go into the geological record of the Catskills, we have found evidence of at least 4 different types of soils. These things called alfisols or forest soils. Entisols are very baby soils. They just start to get a little bit of rooting going on, and they start to differentiate themselves a little bit, and then Mother Nature buries them and shuts them off from active soil formation. Inceptisols, as I had said, are just a bit more advanced. And this thing here, vertisols, vertical. These soils are noted for their vertical shrinking and swelling, what we call pedoturbation, because they're full of clays that expand and contract, the swelling clays, the smectites. In modern soils, sometimes these things expand and contract up to 50% of their original volume. And so the soils can't go lateral as they expand because they're confined by other soil material. And the only thing they can do is just heave the land surface upwards. And then once the soils dry out, they shrink back down. And they can also have very extensive cracking with them as they dry out. And so the soils I have shown here are from a former grad student of mine by the name of Jason Mintz back in 2010 during his PhD years. He saw soils in the Catskills and described them. And I'm not going to go through every single symbol here, but what I want you to notice is he found some that were associated with a lot of fossil tree stumps and was able to make the association both physically, micromorphologically, and chemically with what we would consider a modern forest today. And here's one such soil. One of my former grad students standing out here, he's almost 6 foot tall to give you an idea of scale, but here it is. It's very distinct from channel sandstones below and above. So this would be your overbank mudstone facies, which has been overprinted by ancient soil forming processes. Here is one of our vertisols. And I would ask you once again, what do you see? What grabs your attention as you look at this? There's a lens cap for scale. And my hope is, as you're looking at this, you're noticing these weird smiley faces that are cutting through the rock exposure. These things that you're seeing smiling at you is the direct evidence or the physical manifestation of extensive shrinking and swelling of the entire soil system back when this was the active landscape back in the Devonian. So these plains you see right here will be slick and sided and polished because they represent a plane upon which the soil is just shrinking, swelling, expanding, contracting. And it slices and dices up the soil at the macroscopic level all the way down to the microscopic. And you can see this evidence in thin sections when you study the soil morphology. And so what we're going to do here with this is the first area we're going to look at is something proximal to a stream. Then we're going to jump some of these others. So here we are back in Cairo Quarry in southeastern part of New York State. And you see this person here looking down onto a centralized tree stump with a bunch of roots moving away from it. I also want you to notice this area right here with number 1 looks sort of yellowish, reddish. Area number 2 looks sort of bluish, greenish, grayish. And area 3 in the back there also has like an orange coloration to it. What I came to find out with this is that in surface view here, I was actually looking at a soil composed of 3 different horizons, actually only 2. And then this one here was the layer that covered it and shut off ancient soil formation. I found that all of the tree stumps were at this level right here, the ancient soil surface, and all of this weird coloration you see right here was due to the rise and fall of water tables because we were very proximal to a stream back in the time of the Devonian. How do I know I was near a stream? Because also on this surface, you find a bunch of fossil fish that were blown out of the water and deposited in an overbank setting and just, well, died. And so we have the taphonomic aspects of this. We have the soil aspect to suggest this was very proximal to a river system when this soil and this forest was growing. And as for the forest itself, here we are in Cairo, New York, right there to give you an idea of where we are geographically. But this is a grid map made with drones and photography and just measuring everything out. And the different symbols that we have on here are different types of plants and different type of tree-like species, or things that were growing tall. I don't know if I want to use the word tree, but they were growing up into the air with different size trunk diameters, root balls, root propagation strategies. And so here we have from the Devonian, this was actually published a couple years ago and was proposed as, recognized as the world's oldest forest that was preserved in geological record. I think this is since then it's been taken over by another fossil forest that's been found that maybe a bit older. But the point being, if you have the right exposure, there there are a lot of data in the geological record, both from the ancient soils and also the plant communities that you can pull out to try to understand what the Devonian was like. All right, so we're going to go from a proximal position near a stream. We've already looked a little bit at stable floodplains and some of the forest soils, the alfisols, but now I want to take you down here to the ancient coast. And to do this, what we're going to do is we're going to bounce it down to Virginia, West Virginia, in this area right in here. And in particular, we're going to be going across the structural front. And at several of these stops here, between Harrisonburg, Virginia, and Elkins, are places where I looked at some of the paleosols in association with, what we come to find out, was the coastline. So here we are near Baker, West Virginia. And when you look at this, I want you to notice there's reddish stripes in association with these yellowish tan sands. As we get up close to this stuff and take a look, we find out that a lot of the sands are just full of beautiful ripple marks. These sands have also been classified as shallow marine sands based upon the work of one of my coworkers from several years ago. But we're looking at the transitional area between the marine and non-marine. So let's take a look here. At the Baker section, and again for scale, this is my coworker. He's about 6 foot tall. We got to looking at some of the soils and things within here to see what the types of soils were in relationship to some of these marine, small scale flooding events where they were covering the land again. And what we found was, for the most part, in this environment where land met the sea, most of the soils were less than about a half a meter, and they tended to be not that well developed, what we would call an entisol. Parent materials, or what we call sea horizon material, being barely converted over into a horizon or surface horizons of soils where organic matter is starting to intermix with the geological mineral matter of that soil. Well, okay, that kind of makes sense. If you're on a coastline and ocean levels are going up and down, and you're prograding a little bit, and then the ocean comes back up, it makes sense that the soils would probably be a little bit weak. Okay, well, that's fine. Um, we then went 10, 15 miles away to another paleo coastline site near Augusta, West Virginia, and you can see the same motif again. Reddish stripes, yellowish tan beige sand bodies. And so thinking, that's probably going to be the same stuff. Got up there, started looking around, and it was absolutely totally different. I was finding very well developed soils on the scale of almost a meter thick, many of them. I had these slick and sided features showing expansion and contraction of soils, because here's one right here, here's another down here, here's a part of a plane right here coming at us. These things were in 3 dimensions, like ice cream scoops going off in every direction. Um, this was an ancient vertisol. There were smectites back in the soil when the soil was active in the Devonian that would shrink and swell upon wetting and drying. Okay, I was finding beautiful root traces branching downwards, all suggesting there was a well-drained soil. That's great. And at the very top, I started to find these weird wedges that would go straight down and slightly curve a little bit that were filled with silt that matched the overlying body of sediment that was coming in, capping it, and shutting off ancient soil formation. And as I looked around a bit more inside of this body, I found brachiopods. So here we have a marine associated sand coming in, flooding an ancient land surface, and the materials from this sand body were filtering down into and filling in some of the cracks of this ancient vertisol. Well, how do we do that? Well, first off, here's just some of the classification of horizons. Really not that important for what I'm trying to get across here, but this is what I found to be most interesting, was the fact that we'd actually seen a flooding surface with marine fossils in it on top of our ancient vertisol. And it was creating a situation within which, if you started to combine these sections or follow any one section for a while, as you went through it and looking at vertisols, inceptisols, or vertisols with calcium carbonate in them, suggesting drier conditions, or forest soils, you would see this vertical succession of one going into another. Again, a Walther's law kind of approach to what's going on these dynamic landscapes as they're being buried by overbank flooding events. But what about the vertisols? The smectite inside of these vertisols coming from volcanic activity. The hydrolysis of volcanic ash produces smectites as a secondary byproduct. And so we started to realize that these punctuated areas of seeing vertisols were more than likely associated with discrete input of volcanic materials into this ancient soil system along these ancient landscapes. Okay, not bad. As it turns out, this is going to be something very important to one of the problems I'm going to be raising here in a little bit, related to why the Catskills frustrates me so much. But let's go on here for a little bit because I want to show you something else. So we've got this vertical succession of all these different types of soils, one on top of another, one on top of another. We've seen the proximal to distal locations of these. We've seen coastal versions of these, some more well developed than others. But it gets worse. Because what I need to do is I want to go back up to now a more proximal area, the orogenic front, high mountains. And what I want you to think of is what's going on during the Devonian. As we go from the Devonian into the Mississippian and Pennsylvanian, what do we eventually end up with? We end up with some ice ages. Okay, well, there had been evidence or suggestion of ice activity in the Devonian about a decade or two ago. And it just struck me one day as I was talking to one of my grad students that if there was indeed any kind of glacial activity that might have been going on in some of these mountainous areas, you should find evidence of ancient soils that were affected by periglacial activity. So I sent my grad student out just off of a whim, and he started finding an association with what have been interpreted as diamictites. He started to find these downward cracked V-shaped bodies and also other massive bodies of coarser material that, if you look in the modern, they're ice wedge polygons and periglacial features. And we're in the middle of getting this manuscript together right now for publication, but we're finding all of these things underneath bodies of diamictites that have been interpreted as glacial tilts, which makes sense. Periglacial environments on a landscape forming before a glacier could override that same particular area. And so forest soils, vertisols expanding and contracting as we go up in through or up into the Devonian, even higher towards the Mississippian, we see evidence of frost wedging and periglacial conditions. So there was a complicated story. And here's the diamictite facies that has been mapped all through here. And my grad student was looking here in West Virginia, up here in Pennsylvania. And I want to see he's got one other place down through here right now. But there's ancient frozen soil processes observed in the Devonian, then covered by diamictite, which we assume is glacial till or till-like now. So a lot of complicated ancient soil forming conditions, depending upon where you are along this isochronous landscape. Here's the problem, and this is what the main meat of what I want to present tonight and ask for help, guidance, and or something. Here's the issue. Here we are at Red Hill. But think about any time you've been on any exposure anywhere. Nice, you get good rocks. You got a nice road cut here. You can describe the rocks from top to bottom. And there are ancient soils in here. All these little recessed intervals are ancient soils. There's like 20 or 30 of them here. Down towards this end are where some of the beautiful bones and vertebrate fossils and fish have been pulled out of the Red Hill locality. But this is only good for this area. We can get detailed information, but then what do we do with it? Let's pretend it's right here. That's great. But how does it relate to all the other profiles that you're looking at? How do you establish the chronology, the geochronology of these sites, be it Pioneer, Pennsylvania, with all the beautiful fossil fish and tetrapod stuff, Maybe it's that fossil forest up in Cairo, New York. Maybe it's my vertisol down along the coastline covered by a sand with brachiopods in it. So you have these different locations, all of which represent their own individual soda straws of what you've learned at each location. But how can you hope to match them up over hundreds of miles of exposure and outcrop and thousands of meters of deposits within all of these various basins coming off of the orogenic front? And that is the problem that's really driving me nuts. Because let's just talk about Virginia and West Virginia. And as you look at this stratigraphic diagram here, maybe there's some names that look familiar, maybe not. Now let's go to Pennsylvania. Maybe you like these names better. I don't know. I am purposefully avoiding giving any of these things any kind of lithostratigraphic designation because I don't know which one it is. Is it Four Knobs or the Hampshire that also correlates to, I don't know, the Sherman Creek or Duncannon? Maybe it is. But the problem is, what are we dealing with here? We are dealing with a situation, we are dealing with a depositional system that is prograding and building out through time. And so here's what I would have you think about. Here's our mountains of the orogeny. We're shedding sediments off, and we are building these strata out in a progradational fashion into the basin over here on the left-hand side, which I don't have drawn in because I'm only focusing about on the terrestrial parts right now. What's happening from proximal to distal? We're seeing changes in grain size. We're seeing changes in the amount of energy of systems to move sediments along. In modern systems, we see changes in the partitioning of biological communities, either the paleo or the botany, the critters that are there, whatever. Here's what I have you consider though. Here's our soda straw that we just took as a measured section, say at Hindered, Pennsylvania. How does it match with anything else through here? How do we know? If we go back to the problem of all of our individual soda straws, the issue becomes, we know though where, if you will, but the thing that becomes an issue is the when. And in each one of these sections, as we prograde this sediment pile out, what we also see in modern systems are changes in hydrologic regime. In the more proximal areas, things tend to be a bit drier hydrologically because the water can seep down and also move out across this wedge of material, such that you get to a point down the wedge to where the water starts to become more emergent. We call this the spring line. Things will appear to be a bit more waterlogged, and or the amount of water available for plants to do their thing is going to be totally different than what it was back up here. But as you prograde all of these materials further and further into the basin, what this creates by default is a situation to which down at the bottom of any measured section, things may appear to be more water enriched. I'm not going to say the term waterlogged. Let's just say there's no deficit in water. It has everything it needs. But as you go up, this should produce a change to more well-drained, maybe more what are going to appear to be water-stressed or water-limited conditions, because all you're doing is migrating the facies from proximal to distal. You can see this in any small-scale alluvial fan today. But in the geological record, within these basins of kilometers of accumulation of terrestrial strata, you're seeing this over a very large scale. And so the question I have is, let's go back to Hindered, Pennsylvania. Was that here? Here? Was that here? You got the progradation of all of these facies. It's diachronous deposition from one side to the other. But within it are individual isochronous land surfaces that I call my paleosols. There's thousands of them, tens of thousands. But how do they match up? And so the big concern I have with this is not only in the Devonian terrestrial strata, I also work on this same problem out in the Paleogene strata of the Great Plains. The issue is, how can you distinguish Any upward change from a shift in paleoclimate versus just a shift in the depositional phases and the water budget, which is available. That is what I'm trying to figure out right now. Because as the system progrades, you're just going to see the migration through space and also time of different paleoecological conditions. Why should we care about this at all? The Devonian's rather important. We see vascular plants taking over, stabilizing the landscape, changing the way within which weathering actually occurs within geological material. And as these plants take over, as vascularization takes a grip on land, we start to also, through photosynthesis, take all that CO2 out of the atmosphere, put oxygen back in, and we start to preserve and encapsulate all of this new formed carbon in the form of plants into the geological record. So, if you will, on a very large scale, possibly global scale, what are we doing? We're changing atmospheric dynamics and composition. How does this change Basie's architecture from periods to where there was not a lot of land stabilization versus when vascularization finally stabilized land surfaces? Regional to global carbon cycle, source to sink. We're making all these plants up on land. This new carbon is getting out into the basin. It's being stored. And I could keep going, but lastly, down at the bottom, we're going from hothouse to icehouse transitions as we close out the Devonian, start to hit the Mississippi, and eventually all this late Paleozoic ice age. I would think maybe that the evolution of plants, the storing of carbon, photosynthesis, changing the composition of atmospheres, all related. But how do we understand the timing of this in a system which is diachronous, as its own individual sub-environments migrate through space and through time? These are rather important things. How do we overcome this? How can we link up all these individual sites with their own individual soda straws of important paleoclimatic and paleoenvironmental activity? That's when I bring up this diagram, which some of my former students and colleagues have seen before. I call it the Devonian Wedge elephant because it's quite a story. Um, and depending upon what you do as a geologist, you're grabbing different parts of this elephant. I put the paleopathologist back here because, in a way, the soils that form and that are being preserved in this landscape are functions of all this other stuff and how they've interacted to form the soils that we see. What's the one thing missing from this that would really help us to figure out the spatio-temporal aspect of what's going on during the Devonian? Well, it's that person right there that's got a hold of the ear. It's the geochronology. We know the where, we know the what. What we need is a better understanding of the regional when, given the prograding diachronous nature of this thing we call the Catskill Wedge or the Catskill Delta. So how are we going to get around this? In the recent past, there have been attempts to make use of the tidal geochronology within the Catskill. Dave Broussard has been working on this. We've also seen a big increase in just the use of the tidal zircon geochronology. So what I would have you do is I would have you consider all of those vertisols preserved in the geological record. There's zircons all throughout this stuff. Perhaps, maybe one way to address this is starting to do the tidal zircon geochronology in effort with others who are already working on this stuff. This is why we need a team. And I would make the case that on a grand scale, that the deposits of Catskill Wedge from New York down through Pennsylvania and the Virginias really are, in essence, to be considered a deep time critical zone observatory. Whereas in the modern, we're trying to use critical zone studies to understand how Earth surface processes all interact with each other to give us the Earth's surface that we see. The deep deposits of the Devonian Wedge, they meet a lot of the hot button issues and questions that we'd like to address. What's going on with deep time climate, the landscapes, biology and environment, as all of these things are evolving? And the Devonian is such a critical time for that. And so I attended a session by the Continental Scientific Drilling Community back in October, to where I put forth this idea of the Devonian as a beautiful place for a deep time critical zone in efforts and in hopes of getting some interest amongst the community, um, for accepting or considering a proposal to do some drilling within this stuff. Because individual soda straws by themselves are hard to connect. But what if we have cores at various places that we can then establish or connect through a, a geochronological framework or mesh? And so within this proposal, I was saying or suggesting that it's a bunch of paleocritical zones, all of these individual soils with a lot of important paleobotanical and paleoevolutionary aspects to it. The plants, the animals, stabilization of landscapes. We must absolutely understand how this archive was constructed if we hope to interpret the spatiotemporal aspects of the paleoclimatic and paleoenvironmental signals. If we don't understand how the library of data was constructed, how can we hope to use it to our best abilities to interpret what is going on? And so I like to say we need an understanding of the what and the where and the when for any one of these sites that we're looking at, say Red Hill and Heiner, that fossil forest in Cairo, or whatever other sites might be out there that we've not yet discovered. And so we come back to this, and I need state surveys. I need federal. I need academia to all get together to try to somehow get a grip on this elephant. Um, I know the PA survey has cores of Devonian materials and such, but I'm wondering how can we work together? How can we springboard some of these ideas in order to start addressing some of these bigger questions? Um, and so I guess instead of reading through all of this, I guess how can we tackle this problem? We don't have temporal control to the degree I think that we need in order to understand how these conditions through the Devonian have evolved and what effect they had. So moving forward in the summer of 25, if things work out right, would like to convene a meeting of people to go out and just look at some of this stuff. Tell me what you got. What are your best sites? What are the questions running through your mind related to these strata? In association or in support of this, coming up this spring in Harrisonburg, Virginia, we're going to be hosting a session at GSA, the land of the sea, looking at the Devonian depositional systems of the Appalachian region, trying to figure out what are some of the big questions we have and how can we start working together to answer them. And then also we're going to be doing a field trip out to see some of these exposures in the Baker, West Virginia, the Augusta area. Hopefully we'll get to see some of these paleo paraglacial soils as well. With the eventual goal of developing a proposal for the Continental Scientific Drilling Program, because I think this is a worthwhile goal. Um, it's an archive just waiting to be explored, data waiting to be found and interpreted. And so, as a final gesture, as a final thing, I do not come to you with any big conclusions or revolutionary things, but more of just a, are you interested? What do you know that may be useful for this? Even something as simple as, hey, Rudy has some really good exposures of paleosols that I can go look at. And so myself, in coordination with Chuck Stratton from the New York State Museum up in Albany, we've been working on this together for a couple of years now, trying to get this moving. And so, as a final thought, I would just put out a general plea for help. If you have ideas, please get a hold of me. And with that, I'm going to go ahead and stop talking and take some questions from the group. But thank you very much for listening to me complain about stuff that's driving me crazy and some of these questions that I have. And I'm hoping to get together with representatives of the PA survey, see some of the cores and such you all have, and hopefully move some of this stuff forward. So thank you very much for your time and happy to have some questions.
Great. Well, thank you. Thank you, Dr. I just noticed, well, teams never wonders never cease. So look, there's a Q&A. So those of you online, if you want to use that to put in your questions, can you see that, Dennis? If you click on the Q&A button up at the top, there's a question from Bill on what defines a forest.
Bill.
Can you
Hi,
see
Bill.
that?
Thanks for the question. Um, Bill, that's something to where I'm going to make a very snarky pun of I can't see the forest because of the trees. I'm not sure to what degree there's an actual botanical definition of what a forest is. I've always thought of them generally as am I forested? Do I have a closed canopy? Or am I more open? This is really something of concern to me in the Paleogene, where I'm seeing changes from forested conditions in the late Eocene into more open and savannic conditions without a lot of trees in the Oligocene. And so I think of it more in generalities, but I don't know. I'm assuming there's a botanist out there somewhere that has said this is how many trees you need per square hectare or whatever to make a forest. But that is not a bit of information that I know. Or if there's also particular geochemical aspects that define a forest.
You guys have any questions? Those of you online, if you can find that Q&A button, you could type your question there. Anyone here? Bill.
You mentioned, obviously we know there's a fair amount of volcanism occurring during these times. How widespread was volcanic ash? And I assume the bentonite is kind of evidence of that. Can that be used as some sort of time scale?
Yes. These things went out as far west as Ohio, um, as far west as the Appalachian Basin, the ocean was out there. Um, and based off of just very back of the envelope calculations of thinking like, how many volcanoes were along the system, looking at modern convergent tectonics, say like the Andes, how many volcanic ash events do we have preserved in and around there? How often are they erupting? And there should be thousands of bentonites in these terrestrial sections, or easily seen in some of the marine deposits, like in between some of the carbonates that are out in the middle of the basin. But within terrestrial sections, they're a bit more cryptic. In all the years I've been looking for them, I found two, three by accident. My colleague Chuck Stratton from the New York Survey has been making it one of his life goals of collecting everyone he finds in order to get some zircon dating to where we can do something like, uranium thorium, uranium lead dating directly off the bentonites. Otherwise, given the difficulty of finding these distinct bentonites, I'm thinking the detrital geochronology within these strata may be a way to quickly define what I will call time zones, time horizons, or intervals that we can then start tracing throughout this material, because I think it'll take way too long in a terrestrial setting to find enough bentonites to establish this temporal mesh that we need to answer some of these questions.
Bill?
For an individual paleosol, say on the order of 5 or 6 feet thick, do you have any idea on how long it took to form something like that? Do you have any?
I tried to do that once when I published some of my master's work many, many years ago, and I said because this soil has a B horizon with the following characteristics, it must have taken 8,000 years. And I was slapped down very hard during my first attempt to publish something. And what it comes down to is if we go back to the 5 factors of soil formation, that CLORP acronym, there are times to where a long period of time can pass, but soil processes move slowly, maybe because the soil is waterlogged. Or there may be instances to where a soil, even though it's nice and steadily forming, has a lot of input of new sediment, new parent material. And so the soil builds upwards as it's also trying to modify and become more stable in its soil forming environment. And so the short of this long rambling answer is it can ballpark within orders of magnitude even in modern soils, soils from different regions with the same features can take orders of magnitude of time to form in environment X versus in environment Y. So I try to trend away from like this soil took X thousand years to form, because even in the modern, it's all over the map by orders of magnitude.
Hey, Dennis, back over to the chat. We got a question about the late Devonian glaciers and their advance into the clastic wedge.
I do not see that question. I don't know if I need to refresh.
You got to go over to the chat.
Oh, it's in the chat. Okay, I'm sorry. There we go. Late Devonian glaciers, did they advance into the clastic wedge? Yeah. One of the conclusions that's coming out of this paper we're trying to get published is that we are suggesting that glaciation went further into the basin than previously thought. Based upon our paleogeographic reconstructions, we think we're probably at around 30 south for some of the stuff. Whereas in previous work, people were thinking the glaciers were maybe hung up around 50 degrees south. And so this would suggest that the glaciers were getting farther out than previously recognized. So yes, out on top of the wedge. Don't not making it all the way to the ocean, I don't think, but definitely out into some, at least some of the proximal deposits of the wedge.
All right, we got some more questions in the Q&A section. Bill Roman was trying to get in on that string of bills on the question.
Oh, there's the new post button. Okay, because I use Zoom a lot. I'm still working my way around Teams.
Well, this is the first time we've ever done the Q&A section, so this is new ground for us. But yeah, we
Let's
got.
See, so then from Bill Roman, not a question, but a comment. New significant exposures of the Catskill may be available for study if the PA Turnpike executives or executes the Allegheny Mountain Realignment Project. Ooh, this sounds cool, but here's the problem. What if I said that new, fresh road cuts are a pain in my rear because they haven't had time enough to equilibrate to the modern day environment? And so these differences in erosion rates and weathering rates, and say the channel sands versus the floodplain overbank materials, aren't as prominent as they could be. And so back when I'm going to call it the Route 15 interstate, is it Interstate 99? Is that it? That was coming down from north to south. When they blasted all that stuff out, cool, nice rocks, but it hadn't seasoned, it hadn't matured enough. But I would love to go out and see these new exposures, but they tend not to be as helpful as ones that have been around for a while. Let's see here. And from Gail, this doesn't really help, but Bill did a state map project across several quads in Northeast PA, trying to find members in the Catskill without success. There were no key beds to follow. It's just a mass of fluvial deposits. I feel your pain. We did a fairly deep bore that we thought should hit the base of the Catskill into the lock haven, but I think we didn't catch the contact. Bill would know more for sure. That statement, Gail, is exactly what I feel every time I go out and I look at these strata and I go, oh, Devonian Catskill deposits. Someone will ask, what formation is it? And I'll go, yes. I don't get it, how some people are calling some of these formations and or members within this stuff. And I think some of my inability to grasp it is because of the degree or the number of state line faults in between Virginia and Pennsylvania and New York. And what's one thing here may be called something else over there. But I do feel your pain. It just looks like a massive fluvial deposits. And what do you do with it?
Hopping back over to the chat, I think Chuck's in mid comment.
And then I see Jeff Prop put something up. What is the age control for the paleosols that indicate ice influence? I wish I knew. We don't have any age control of them yet, other than they're just beneath the diamectites that have been described by Brzezinski. What's the possible age range? I wish I knew. Perhaps cold conditions may have started prior to deposition of the specticop. I absolutely think that the cold conditions were preceding the presence or the deposition of the diamectites. We see that in modern day glacial systems, all the paraglacial systems, permafrost systems associated with any glacial activity around the globe. And so, absolutely, the colder conditions were there before the glaciers made their depositional footprint known.
All right. Yeah, Chuck was apologizing. He was cutting in and out, some connection issues. So, Dennis, this was awesome. Thank you so much. You're going to have to come and visit us at some point, but I'm glad we were able to have you remote in. It seemed, with some of the technical challenges, it seemed to work out all right. So, let's give him another hand.
Yeah, this is awesome. And then if I see this feature correctly, I see that it looks like Chuck is in the #1 position to ask a question. I don't know if the studio audience, the people online, have the ability to unmute and ask the question. But assuming we have some time available, I guess I would ask, hi Chuck, how you doing?
Well, actually,